Excellent. Well, good to see everybody here bright and early. My name's Dave Cole. Been here for the week. I guess I've met a lot of you. The only error I'll point out is I'm attributed to being at the Army Research Laboratory, which is a different organization. I'm actually a retired but still affiliated with the Army Cold Regions Lab in Hanover, New Hampshire. Mark Hopkins, formerly of the same lab, now on his own with a company called Real Ice. And Mark and I have actually worked together for quite a few years on everything from snow mechanics to granular media mechanics. I'm kind of the experimentalist and he's the DEM implementer. And Mark is going to give a talk using DEM to model ice sheets and structures. Same format as before. We'll have about 45 minutes of presentation, 15 minutes of questions. Go ahead, Mark.
Thanks. Except I would say you're more the experimentalist and I'm the
numerical geek.
Numerical. What's the word?
Implementer, right?
Yeah. So thanks, Alexi, for inviting me. Very nice here. So this morning I'd like to talk about ice encroachment. First I want to thank my co-conspirators, Kyriska, Rubber Bridges, without which this work wouldn't have been done.
Mark, I think he needs to mic you up.
Yeah.
Sorry if we neglected that.
Definitely.
Please repeat what you just said to the mic.
Okay, is that better? So what is ice encroachment? Ice encroachment occurs when you put a structure in an ice field. So this is an ice island in the Caspian Sea, and it's not too easy to see, but you can see the piles of ice around two sides of the structure. Over here, there's a little bit of encroachment. What is actually encroachment is okay. Okay. Encroachment actually happens when the ice goes onto the platform. So we don't count the stuff that's piled in front of the platform, just the stuff that's on top. Because that's the ice that's going to bother the people working there and maybe even injure some of the equipment on the platform. This is just the same picture but without the writing. You can see that pile up a little bit better here. And over here it's even starting to pile up on the pad. See some of the equipment surrounded by the ice. So what we want to do is understand this process a little bit better and then possibly build a tool that we can use to kind of design mitigation measures. So we started out in the laboratory at HSVA, and we performed some tests with saline ice sheets, and the tests were really successful. I mean, I come from an ice ridging, pressure ridging background, and we were never able to create, at least early on, never able to create good ridges in the laboratory. What we got was just ice crushing and a lot of pulverized ice in front of the structure. Or rubble fields that spread out from the structure, but we were never able to get the stuff to pile up, the ice to pile up on the structure. But using this saline ice at HSVA, they found the secret, and we got beautiful pile up on these structures. This is a model structure, but in full scale, this is like a 10 or a 12 meter pile. So it's pretty big. I think the ice sheet was full scale 90 centimeter, but I think 6 centimeter was the actual model scale. So this is where we started from. So this was to kind of get our inspiration for the simulations and the computer modeling that we're going to do following this. So what is computer modeling of ice encroachment? First of all, it's discontinuum mechanics. We're not modeling a continuum, we're modeling something made up of discrete pieces, ice blocks. Our mathematics is pretty simple. Just F equals ma. But we're going to do that at every contact between every pair of ice blocks in the entire model. And we're going to use a discrete element modeling approach where we model individual ice blocks. Okay, just to show you a little bit about what discrete element modeling is. This is a long cascade of individual ellipsoidal grains. And what we're doing is, at every time step, which is on the order of a millisecond, we're going to find the contacts between pairs of grains in that pile and find the force between those two grains, calculate the force, then integrate the motion one time step. Once we've got the new positions, then we find the new forces based on new overlaps between grains, calculate new forces, new positions, and we just force motion. Position, force, right? For, however many millions of time steps. Okay? Yeah, I should mention this was first begun in the 1960s at Lawrence Livermore National Laboratory with these guys Alder and Wainwright. They were doing molecular dynamics calculations. It was first applied to quasi-static systems like rock systems by Peter Kundal at, I think it was in London. I'm not sure if it was University College or Imperial. But anyway, it happened here in London. Okay. So what we do is we store the shape, position, orientation, and velocity of each grain. We have in 2D 3 degrees of freedom and 3D 6 degrees. The dynamics of the system evolves from the contact and body forces, just F equals ma at each contact. Do a forward time stepping, we calculate the velocity at the half time step based on the force, and then the position at the full time step based on the velocity at the half time step. Simple. Particle orientation is specified using the quaternions. In this talk, we're going to talk about 2D polygons and 3D polyhedra, and they're defined by vertex vectors from their center of mass. Okay, this is what a 2D simulation of entrainment or encroachment looks like. And this is a vertical slice through it. So it's like 1 meter wide. Each of these red blocks is 1 meter, is a 1 meter square block. The freeboard is like 4 meters. The draft is 5 meters. And this was patterned after the Kolompka structure in the Caspian. So here's our intact ice sheet in yellow. And that's pushed into the, first initially it hits the structure. And we don't have any crushing in this model, so what happens initially is bogus. You're going to see a little chaotic breakage and so forth, but once you've accumulated a few blocks there, the sheet is able to ride up on the block accumulation, and then it begins to fail in flexure, which is what the model is designed to do. So initially you create this pile of rubble in front of the structure, which allows the sheet to ride up, and eventually it rides up onto the structure and puts these ice blocks on the structure, and that's our encroachment. So the only thing we're going to call encroachment is what is resting on the structure. This is a picture of the ice sheet in the model. It's made up of rectangular blocks, individual blocks. The blocks are glued together with a viscous elastic glue. When the tensile strength at the top or bottom of the sheet reaches the breaking point, then a crack propagates across that joint in real time. It doesn't happen in one time step, it happens as the stress propagates through the joint. We also have a little damper on the sheet which decreases exponentially towards the tip, and the purpose of that is to keep the shock waves from traveling down the sheet to the boundary and breaking the sheet catastrophically. Okay, so here's the beginning of the simulation. Here's the sheet and the structure. So initially you get this bogus breakage because there's no crushing in the model. But give it a little while. Now we've accumulated some rubble in front of the structure, and it's starting to do its thing. So first it has to build this platform in front, and then a ramp up to the structure. Now everything's going smoothly. Whoops, it buckled. It's having a hard time pushing the ice up that pile. Still going. Naturally, I picked one of the more photogenic ones, so they're not all like this. Okay, now it's going to have a hard time getting through that rubble. So this is the problem with a 2D simulation. Once you've got an obstruction, it's really hard for that sheet to move that obstruction out of the way or climb over it. Whereas in 3D, where you have non-simultaneous failure, you've got the supporting sheet on each side of the obstruction that can help push the sheet that's blocked over the obstruction, you might say. So I just wanted to keep that in mind for later. But it is one of the downsides of the 2D simulation, that when you have an obstruction, that's it. So we did a whole bunch of simulations. Here's our parameter space. We've got ice thickness, 30, 60, 90 centimeters, strength, 450, 750, 1,000, kind of a weak ice sheet, a medium ice sheet, and a strong ice sheet, and a freeboard of 3, 3.8, and 4.6. And these were chosen with the Kalamka structure and the Caspian in mind. The first thing we looked at was the IE stands for ice encroachment, so that's the ice on the platform. The dependence of ice encroachment on strength and thickness. So we have strength on the bottom axis from 450 up to 1,000. And V over V max is it's the encroachment normalized by the maximum encroachment that we saw. So, I'm sorry, it's the encroachment divided by the mass of all of the ice pushed at the structure. So 30%, if it's 0.3, 30% of that ice ended up on the structure. So at the low strength, you've got a weak ice sheet hitting a structure. It doesn't have the strength to push itself up the pile onto the structure, and you don't see much encroachment, less than 10% of the ice. At the medium strength, more ice encroachment. At the high strength, a lot of ice encroachment. There's three separate slides here. 0.3 millimeter thick ice, 0.3 meter, 60 centimeter, and 90 centimeters. So thin ice to thick ice. So the thick ice has a lot of encroachment. Again, it's strong ice. You can push a lot of ice up the pile onto the structure. With thin ice, you push almost no ice. So encroachment increases with strength, and it increases with thickness. Now we're looking at the strength and the freeboard. So how high is the wall above the water, which we're pushing the ice over? So we've got freeboard of 3 meters, 3.8, and 4.6. So there's a little more encroachment at the lower wall, 3-meter wall, than there is at the 4.6. Again, not surprising. You're pushing the ice up a bigger wall, so you'd expect less encroachment. And again, there's the same dependence on strength on the bottom axis. Okay. So now we want to look at the maximum pile height, just for intellectual curiosity. How high of a pile can we make? I know, I forget who was talking the first day. He was talking about 14, 15-meter piles. And hard to believe, but it's true. I mean, these piles get pretty big. This is 90 centimeter ice, 460 meters of ice pushed at the structure. That's not that much ice. And you can easily push a kilometer of ice onto a structure with a 3-meter freeboard right here. And this has almost a 15-meter pile height. But again, with the 2D simulation, we might run 10 of these simulations, and we might see one with no pile up, one with 2 meters of height, one with 5 meters, some with 10 meters. So there's a large degree of scatter with a 2-meter simulation. Okay, so the maximum pile height, depending on thickness and strength. So here's our thickness, 30 centimeters, 60, and 90. or strength, weak ice, medium, thick ice for all three. And not surprisingly, the maximum pile height goes from 6 meters to 11 meters to 16 meters with the 90 centimeter ice. So the thick ice and strong ice, you can truly get a huge pile. So we were thinking a little further. Supposing we increase the freeboard to 10 meters. That's the vertical wall, the height of the vertical wall above the water. The guys that build the structure aren't going to like it because it's going to cost a fortune. But just what if? And what we found is that, of course, the encroachment decreases, but this pile height remains constant. I wish I could. You can actually take that structure and move it anywhere such that the point is tangent to that the sheet. You can move it right along there, and you can imagine. I can't hand wave my way through this. Sorry, but as you decrease the freeboard, the encroachment increases, of course. So, but it's interesting that the pile height does not depend on the freeboard height. Just as an intellectual point. But this is the encroachment now. This is the ice that actually makes it onto the platform. So we got two lines, the maximum and the average, and this is for 90 centimeter ice. The maximum, and again, this is the fraction of ice that's pushed at the structure, which actually ends up on the structure. You can get a maximum of 70%, we saw, down to an average of around 35%. But that's at the lowest freeboards at 3 meters. And you get up to 10 meter, you're down to below 5% of the ice on the structure. So really, there's a big win for making the structure tall if it wasn't so expensive. Okay, so back to those tests at HSVA, the model tests, the physical model tests. This is profiles of the physical test here. The maximum sail height's around 12 meters. This is a 3 meter freeboard, 5 meter depth. This is the grounded portion in front of the structure. Unfortunately, this is flipped around backwards, but it's the same idea. This is the superimposed profiles of 10 simulations. And again, you've got about the 12 meter sail height, the grounded portion in front, and pretty much quite a similar extent, like 30 meters versus 25, 30 meters. So the profiles look pretty good. But you can see the scatter. These are 10 different simulations, and you can see there's a lot of scatter. But the red line through it is the average. Okay. And then looking at the forces. The forces from the physical model are on top. The red one is the force, the normal force on the structure in the direction of ice push. And the blue force is the weight on the structure. So this is the model, or the numerical model. And again, the red line is the force on the normal force on the structure, and the blue line is the weight on the structure. So you can see right away there's a very different character between the model, the numerical and the physical model. The physical model has these distinct ice push events where the force starts out low, rises, and then falls. These are correlated to individual buckling events in the ice sheet approaching the structure. So the numerical model is really, really noisy. You don't see these discrete push events. You see a long period initially where it's just filling in the area in front of the structure. When it finally gets to be riding up onto the structure, you get a higher force, but you still don't see that qualitative rise and fall. However, the magnitudes are pretty close. You know, peaks around 7,500 newtons versus something on 7,500 Newton average. So and the weight's very similar. So magnitude-wise, we're not doing too bad, but there's a different character. That was 60 centimeter ice, or that was 90 centimeters. This is for the 60 centimeter ice. Again, the profiles for the physical model and the numerical model. They don't look too bad. The forces, again, in the physical model, you've got the rise and the fall, sort of regular intervals. In the numerical model, this one actually has a few episodes of rising and falling. You notice it drops to 0 between them because the buckling's occurring way out in front of the structure. Once it buckles, you're just pretty much decoupled for a second. Whereas in the 3D physical model test, you've got a little buckling over here, but you've still got force transferred through the rest of the sheet. Then you have a buckling event over here, but you've still got force through this part of the sheet. So you never see it drop to 0.
Could you try to get the physical parameters in the model the same as the physical parameters in the numerical model and physical model? You tried to model the exact same thing. These are sort of like with like comparisons?
As much as we can, yeah. Yeah, friction, well, you make a guess.
Like, for example, did the numerical model at physical model scale, or did it model at full scale?
These were done at full scale and then scaled down. Yeah. But that brings up a good point. Like, suppose you want to model to match the modulus. In this 2D model, if we crank the modulus up to 1 or 2 gigapascals, we get brittle behavior, and it just doesn't look real. So we have to artificially dial the modulus down to 100 megapascals in order to get non-brittle failure. So that's the one big shortcoming or allowance that we have to make for the numerical model. I'll mention that again later. Okay, so if you were able to get inside this ice mass and actually see what was going on, what you would see was force chains being transmitted through the ice blocks, through chains of ice blocks, into the ground, carrying the weight of the structure, and into the structure itself for the force pushing on the structure. So that's what this simulation is trying to show. So what we've done is color the force black. The thickness of the line is proportional to the magnitude, and the direction of the line is the direction that the force is acting in. So again, we've got this initial period where kind of ignore. But you can already see force chains going down into the bed, carrying the weight.
What are those black lines?
Those are the forces. Thickness is the magnitude, the direction is the direction of the force.
So just normal force.
No, also sliding force.
Oh.
So you see sometimes the directions are oblique, so that's a bit of sliding component and a bit of a normal component. You can see it easier in the aggregate when you see the things line up, the chains. I could pause this thing. Well. So I think this shows it rather well. I mean, you've got your vertical columns that are transferring the weight into the bed, into the structure. And then you've got these horizontal columns that are the load of the ice pushing on the structure down here, smaller ones up here. And then the load in the sheet, which is, of course, the highest, well, pretty high, that whole load is coming through the sheet. So once that load reaches the buckling strength of the sheet, then it buckles, and that's the end of that push. So. Okay, so some conclusions from this 2D modeling. And I kind of mean this to be taken pretty qualitatively, like it kind of tells you what's important in ice encroachment. So the maximum pile height increases with increasing strength and thickness. The volume of encroachment increases with strength and thickness. The pile height is independent of freeboard height. The volume of encroachment decreases with freeboard height, so the higher we make our wall, the less encroachment. The pile height maximum is insensitive to friction. We checked a range of 0.2 to 0.45. The volume, we also did a little fun thing. We changed the density of our ice, so it was barely floating. at the highest, and that didn't make much difference. You still had your sheet stiffness, and you're still supported by the ice underneath. So once you've got that pile, it really doesn't matter how dense your ice is. Initially, when it's floating, well, if it sinks, then you've got a problem. But so once the maximum pile height is reached, then the subsequent deformation enlarges the pile in front of the structure, and you get a rubble field in front of your structure, of course. So that's the 2D work. So we started recently working in 3D, and it's a 200-meter wide structure. The sheet is 90 centimeters thick, and 3D is just a different beast. We're pushing 500 meters of ice at this structure. Actually, no, that was 250 meters of ice. Okay, the same thing from the side. Pretty chaotic because you're looking sideways at the entire pile. But notice how compact it is. The 2D is not compact, and that's one of the big differences. That the 2D would be out all the way out here at this point, and it would take much longer to start putting ice on the platform. It makes you feel sorry for the platform. Pretty rough. Okay. So this is almost impossible to see. This was a sketch that a young student working with Kai made, Kai and Rob. I don't know whether you can see any of it, but this is a timeline. And what it shows is the breaking, this is the time zero. There's these arcs that are drawn across this is the channel. She drew what she tried to do is draw the buckling events. Like when she saw the sheet buckle, and you could see a crack across the sheet, or partially across the street. She tried to draw that and show that as time progressed, the buckling event, here was a buckling event, here's a buckling event, here's a small one. Some of these are invisible. I should have gone over this with a marker, but sorry. Anyway, what it showed was the chronology of the buckling, and it showed that it was non-simultaneous. It went back and forth, middle, the sides, so forth. So I want to kind of show that in this numerical simulation. As a proxy for those lines, watch the blue of the water when the sheet gets submerged. So you don't see a uniform line across the structure. You see very clearly a non-simultaneous buckling going on. So this is what we get what we get from doing the 3D model. Is we get away from that. I hate to use the word called 2D simultaneous failure because it's kind of obvious, but you get into the ability now to model non-simultaneous failure, which is so important in this process. You're standing up already? You're just stretching now, aren't you?
Do my yoga.
Okay.
Yeah,
I was worried about
this is your 15-minute period. So.
It was only half an hour.
Oh, I'm sorry.
Sit down. You have one of those watches that tells you to stand up. Okay. Sorry, Dave. So, three-dimensional ice modeling. Ice sheet begins with a Voronoi tessellation. The sheet has uniform thickness. The adjacent grains are glued together on each, so the joint between two grains is a rectangle. The rectangle has 10 connection points, which are located pretty much at the top and the bottom of the joint. So the relative motion between the adjacent joints, either tensile, compressive, or shear, strains those contacts, those connections. And the force is proportional to the strain in the connection. It loads linearly, and when it reaches the tensile strength for an individual connection, it unloads linearly. So it doesn't break in one time step, there's a softening. The stiffness is proportional to Young's modulus divided by the average grain diameter. When the stress reaches, okay. And we've got buoyant forces and righting moments acting on the grains.
How big are the Bornard tessellation?
What?
The thickness?
Sorry?
How big are the elements compared to the ice sheet thickness?
Okay, because it's 3D, and you're going to model an ice sheet that's a kilometer long and a half a kilometer or so wide, the best resolution I can get on this is like 2 or 3 meters, average diameter, compared to, say, a 60 or 90 centimeter thickness.
So a little more. Yeah.
Quite a bit more, yeah. Yeah, I mean, I'd love to go down to a meter, but I can't do it right now. So what we can do a lot of things with a 3D model we couldn't do with a 2D model. One of them is we can model an oblique push. This is the end of a simulation at 60 degree angle. We looked at 0, 10, 20, up to 65 degree angle pushes. We kept the amount of ice pushed perpendicular to the in the direction perpendicular constant. So the same amount of ice is going into the structure in each case. The ice speed in the direction of the push was 0.5 meters per second. Okay. Okay, so this is a simulation at 60 degrees. We're going to push 250 meters of ice. Because it's 3D, and because we now have non-simultaneous failure, the ice doesn't behave brittly. It doesn't appear brittle. It's not as sensitive to that. So we're able to actually bump our modulus up to a real value. So, which was satisfying. Whoops. Yeah. Initially, we still don't do crushing though. So initially, you got this bogus breakage. But very quickly, we have a rubble pile established in front of the structure. Now you can see the ice is flowing past the structure at a 60 degree angle because you can see the wake. It's quite oblique. Now you've already got some encroachment. It was kind of amazing, even at 60 degrees, that having this degree of encroachment. I would have thought it would all go by, but it's not the case. I should mention that the boundary conditions are constrained. It's not free to expand on the sides. That would change everything. If it was free to expand, I'm sure it would. Everything would be diverted around the structure, most of it. But because the sides are constrained, it's not free. Okay. So this is a table of our data, or our results. On the left is the angle from 0 up to 65 degrees. The velocity in the direction of the structure is v sub x. The transverse velocity is v sub y. So that went from 0.50 to 0.2, 0.45. So most of the velocity is going transverse across the structure. The forces, the force on the structure normal to the structure and the shear force on the structure is F sub y. So you see the normal force going from 60, got some scatter here, down to the 30s. So the forces are pretty much cut in half. Not surprising. And not surprising, the transverse forces increased from close to 0 to, this is probably just a random number anyway, up to about 20 meganewtons at the biggest angle. The encroachment, interestingly, starts at around 12 and goes down to 4. So there is less encroachment, but still significant amount. So the second thing we looked at, which was to try and find some mitigation, whether we could design mitigation measures. We looked at several things. We looked at convex structures, concave structures, arched structures. What we finally, the last one, or the one we tried, which really works, is this: piers. So this is a 200-meter wide structure, and the piers are tetrahedra, anchored on the. We have 5-meter draft. The tetrahedra are anchored at the bed. There's 10 meters of freeboard above the water, 5 meters of draft, and we're going to use 90-centimeter ice. So this is a picture of, we tried 1, 2, 3, 4, and 5 piers. This is one lonely pier out here in the front, and as you can see, it didn't have a whole lot of effect. Most of there's a lot of encroachment, a lot of pile up here. Not too much piled up around the pier. It's a 500-meter push, 90-centimeter ice. So this is 5 piers. They're not lonely anymore. I can't even see some of them. They've got so much ice piled up around them. And you see the pile is now around the piers. There's nothing on the structure. There's not even much in front of the structure. So this is just a comparison. At the top is 1 pier, 3 piers, 5 piers. So you can see the variation. It's pretty systematic. You've got significant encroachment, a little bit, none. You can see there's very little intact ice even making it past the piers. So the spacing between these piers is 40 meters, and the characteristic length of this ice is 10 meters. There's probably some correlation between those two. But look at all of the action is happening at the piers. And I've got to believe that if this continued for another 1,000 seconds, that all the rubble would form out here, not ride up over this pile. It's just too big of an obstruction now. Okay, so this is a table of those results. On the left is the number of piers, and the force on the structure is 100 meganewtons at the base case, going down to something like half. So you still have a force on the structure, but it's mainly the pile, the weight of the pile pressing on the structure in front. Forces on the piers, again, these are average forces, not peak forces. The force on the pier goes from, of course, 0 up to quite a low value, 3 or 4 meganewtons. And that's on all 5 piers. This is on all the sum of the 5 piers. So the forces are quite low. Again, these are average forces. The peak forces are on the order of 20 meganewtons. The pier spacing, 100 meters down to 40 meters. The encroachment now, it starts out at 2 million kilograms down to 0. And remember, this is a 10-meter structure, so the encroachment is somewhat low to begin with. It's because it's such a big, tall structure. But still, the fact that you've got 0 is kind of interesting. Again, it's the characteristic length was 10 meters, 4 times the spacing in that case. Okay. So, just to recap the difference between 2D and 3D. When a 2D sheet encounters an obstruction, it stops. In 2D modeling, there's so much scatter in the results, you almost have to take a Monte Carlo approach and average 10 or 20 simulations to get something approaching average behavior. And that average is somewhat questionable too, except maybe qualitatively. When a 3D sheet encounters an obstruction, the remainder of the sheet continues to progress, so you have non-simultaneous failure. The ice sheet, 3D sheet, smooths the write-up process across the whole width of the sheet. You've got a failure event here, an intact sheet here, failure event here, an intact sheet here. So in total, the behavior is sort of averaged. So a single simulation probably is a better approximation to the average behavior than a whole number of 2D simulations. Of course, you're better off doing more 3D modeling too. So the final answer is, can we now improve structure design using this tool? I think we can. I'll stop.
Nicely done. We have plenty of time for questions. Yeah.
First question regarding when you have the spheres and then you presented the load, global load. Why is the load when you have 3 piers is higher than you don't have piers at all? If you go to this table, maybe I misunderstood something.
Yeah, well, there's no piers, so there's no load on the piers.
But if
Yeah.
could you come to this? Here. Yeah. If you look at this 0 number of piers, 104 meganewton, and then 3 piers, 106.
Yeah,
The variation?
it's probably there's some variation in there, some scatter. Oops. Okay, so there's scatter, and I think it's also the amount of the sheet can actually still get to the structure with 3 piers, whereas with 4 and 5 piers, the sheet never gets to the structure. All the force is on the piers, and the piers are so effective at breaking the sheet that the forces are quite low. It's not like an immovable object and an irresistible force. It's a nice incline which just breaks it in flexure. So
And one more. This is for 0 degrees.
0 degrees, that's right.
So if you're coming oblique loading,
That's a good question.
then you have much more exposed width of those piers probably. So they're not breaking.
A little bit more, just because of the shape of the tetrahedra. But
But tetrahedra, maybe I don't understand it in English. Could you draw it on the blackboard? What would it be?
3-sided pyramid.
Okay, 3-sided pyramid.
Is it 3 or 4-sided?
4-sided.
four-sided.
Well, 4 faces,
Yeah,
but
there's a back face.
pyramid is 3-sided.
Okay.
triangles.
Okay.
4 triangles.
Yeah, thank you very much.
Dev, you had a question next.
Yeah.
Okay.
How do you calculate your characteristic length? By the formula that is there in the elastic, equations of the. Do you do the test by like
No.
you do it in the
No,
basin?
no, and it's funny because when I put that in there, I Googled it and got your paper.
Okay.
And I found the bending formula,
Uh-huh.
but I didn't. I used the classical, kind of the Hiteni or whatever.
Okay.
The
And-
fourth power of the
I've got
modules.
a couple more questions.
I'll give you one more, then we'll go around the room. Okay, I don't want to get it spread around. There are
the-
others.
Because that's an important parameter because somehow, not in the 3D case, but in the 2D case, buckling limits the process. Buckling force is important.
Yeah, I would prefer to do it the way you did it. Actually, bend the sheet, because there's so much uncertainty because of the Voronoi tessellation and so forth. The classical formula probably doesn't strictly apply. But I think your bending is that's the effective
And do you find
value.
penetration of ice sheet through the rubble?
Yes, some
Okay.
cases.
Some cases.
Yeah, right through the rubble. Then you see the recirculation inside.
Yeah. You also mentioned that. Sorry, I'm.
This will be
exceeding
it.
that.
Then we'll move on. That's all right. Go ahead.
You also mentioned that non-simultaneous failure, and this was first introduced by Izu Miyama in one of the IHR.
I'm probably misusing it.
Sorry.
I hope I'm not misusing it.
No, he sort of modeled the ice sheet as it is approaching a conical structure, that there are non-simultaneous failures, because the failure of an ice sheet as it lifts up is localized and it's not across the whole width of the structure. So you may want to consider looking at that simulation. Okay, I give.
Your turn. Yeah.
Mark, me, yeah. I remember you did this experiments with the flat ice and also ridged ice, the DEM simulation some time ago. I just wonder if you introduce the ridged ice in your simulation, would it make a difference?
The ridge height?
Ridged ice, not only flat ice, not only level ice, but ice with ridges or ice of different thicknesses. You know what I mean?
You mean make ridges?
Yeah, yeah.
Have ridges in
How
the
do you do
incoming
simulation?
sheet.
Because you also do
Oh.
rafting basically. Most of the mode is actually rafting in your simulations, right?
You mean actually push ridges at a structure?
Well, no. If you have ice of different thicknesses,
Yes.
right, you can create the
Oh.
more like ridges rather than raft.
You mean non-uniform ice?
Yeah.
Yeah, no, I haven't done that.
You have another.
That would be another interesting thing to do, because that made a huge difference in 2D.
Can I ask a very quick question? Let's just follow up of the question of the gentleman. So you have actually alternating loads. So we have odd numbers of the piles. You have higher loads. If you have an even number of the piles, you have low loads. If you look at your table, the alternation of the numbers.
Yeah.
I'm just curious. Maybe something to do with the end condition around the structure.
Did it have something to do with what condition?
The end condition. Because I don't know how you break when you introduce the piles in front of the structure. How you do it? So you just split the whole distance in equal.
Well, you've got a 200-meter structure in a 600-meter channel, so there's a lot of ice beside the structure. But I'm still not sure what your question was.
Oh, I mean, in your table, you clearly loaded some kind of alternation. If you look at that, so odd numbers, yeah, for here. So if you look one, it's 104. You look 3, 106, and 539. If you go for the even numbers, they're lower.
What alternation?
The column with the structure force.
One is one of
Second column.
Second, well, there's some scatter there.
no.
It's an average force.
It's an average force.
Yeah, number of PS. If you have an even number of
Okay.
PS, you have low values basically, right?
Yeah.
Yeah.
Yeah. Well, that's the way it comes out.
I just curious. But the point is, that's one simulation per
That's
condition.
one
It's not an
simulation.
average of numbers, so there's a
Yeah.
And
stochastic element.
those average forces are over the last third of the simulation, so there's quite a bit of time averaged in there. But still, it's a qualitative. Qualitatively, it means. I guess it means something. Qualitatively, the only thing I would take away from this is that the forces are reduced as you add more piers.
Okay, Claude, I think next.
Fantastic work. Congratulations. It's really, it's
Thanks.
great. I think we need, I'm sure that you had to work on all kinds of details to make this go.
A few.
But once you do, you get to do experiments with a level of insight that you just can't do any other way. And of course, you've got to compare with full scale and model scale, but you really get a chance to look into the problem. So, it's fantastic. My question, though, is just wondering, there's so much that you could study the model itself before you study the output of the model. You know what I mean? What you might call validation work. I mean, you hinted at that. I'm just wondering, for instance, if you were to do just a plate bending test with a point load, how would your model compare? If you were to look at cusp formation on a simple braking, how would your model compare? Things like that. How much? I know that you can spend a lot of time doing that stuff, and you've just got to get on with the project. I get that, but I just wonder how much that kind of thing you've done and where the weaknesses are.
Yeah, I've done a little bit of the bending because, like I mentioned with Dev, that I would prefer to get my sheet properties from bending rather than from theoretical values. One problem is that the 3 to 4 meter resolution is pretty damn coarse,
Right.
but that's a limitation of the computer.
What are you running on?
This thing. Yeah, I mean, it's not hard, obviously, to rig up a point bending test. that I've done, and I've used that to get my to try and correlate the bending strength, the effective bending strength, with my input value, which is the tensile strength at the connection. So
Well, what about buckling?
buckling again follows from that connection, those connection points,
Have you been able to validate it somehow?
the buckling strength.
Yes.
Yeah, so what I wanted to do with the bending test was correlate the buckling strength with that input value, which is the tensile strength of the individual connection.
Did you
And it does.
compare your results with the classic quasi-static
Yes.
buckling formula?
Yes.
And what about dynamic buckling? Because it's obviously dynamics in this. Probably you didn't.
I don't know what to say about that. That just happens.
Yeah. What's the added mass from the ice sheet against your particles? That from
mean the
water.
water.
What's the hydrodynamic added mass?
There's no added mass in this.
There's no added mass.
No.
You'll, clearly at higher velocities,
Yeah,
you can't get it right, I'm sure, in terms of dynamic buckling because there's a hydrodynamic added mass effect. Although that's anyway. It's
yeah, but that's pretty much in the initial bending. Before you get the rubble.
Right.
Once you got all that rubble there, I don't think the added mass is that important because you're sitting on a rubble pile.
Oh, what? No, true. Then I'm
Okay,
talking
Connor,
about the
I
sheet
think
itself.
let's
Yeah.
let a couple other people have a shot. Dimitri, I think next.
Thanks.
Thank you very much for this excellent presentation and excellent task and so on. I tried to follow your works during the last 15 years, and all your works is very, very fine. Thank you very much for this. Two questions, if possible. First, very simple. Do you introduce the clearance processes before the structure due to water current? Ice drift we have together with water current. And so
No currents.
clearance processes is much more easier when we have more or less strong current. What in your model?
No current.
No current. And so no clearance.
No, we try to keep it simple.
Adequate. Okay. And another question. I am quite surprised that the height of final encroachment mass is about the same for small friction coefficient 0.2 and for larger one
I was-
0.45.
I was surprised too.
Yeah, but what do you see? What do you think about the energy explanation possible? One, when we have the same ice rubble, we have the same accumulated potential energy for those. Okay, we have the same amount of ice coming from sea to the structure, but when we have high friction coefficient, we spend a lot of work, a lot of energy to overload this friction
And
resistance.
so your forces go up.
Where is the difference in energy in these two situations? The same final encroachment, the same amount of ice coming, but very difference in work spent for friction.
The forces are a little bit higher because the energy, you're doing more work on the pile.
Doesn't have a finite energy budget.
Where is here?
Oh, the forces. We have as much force as we need.
have relative motion of blocks over blocks.
Yeah.
So this is the energy spent for friction. No force here.
Right, but we have a sufficient force pushing the sheet.
Yeah.
So if the force needs to be 100 newtons, it is. If it's 200 newtons, okay.
So
We specify a constant
the
velocity.
force coming from the sea is
Yeah.
much higher in that area.
Yes.
But why we have now another accumulation of blocks, not at the height of this encroachment, but before the height?
I don't understand.
Okay.
Maybe let's get the rest of the
Okay, yeah.
questions and you can follow. I've ignored the back three rows. Okay, go ahead.
Thank you, Mark. It was a lovely talk.
Hey, Dave.
To what I think are short questions. Okay. So in the 3D simulations, I think you said your element was around 4 meters in size.
Yeah, 2 to 3 meters.
So I'm just wondering because, like, when you get to 5 piers, suddenly you've only got 10 or 12.
Wait, can you speak up a little bit?
When you get to 5 piers, you've only got 10 or 12 elements between the piers.
That's correct.
So I'm wondering whether, I know it's computationally expensive, but when you're only using a laptop, right? So do some calculations at higher at small elements to see if these results
Yeah,
are
I'd
robust.
love to.
Yeah, but it's not.
I don't know, I mean, I've probably got only four elements between pairs.
Well, yeah, because you see some. I mean, and it's difficult to interpret because there's a lot of variability. But you do seem like a big jump between 3 and 4 and 5 pairs.
Yeah.
And kind of, if I was looking at numerical results from an output of a model, I'd be thinking about convergence issues. So, the other question is a physical one. When you compare the 2D simulations, the HSVA lab experiments, you saw the spiking in the forces, and you associated that with individual buckling events, and no doubt you're right. But one question I had was, what about the incorporation of stick-slip friction? You're probably using a constant coefficient of friction. If you use a rate of state law, you could get some peaks in forces. We have found that when we've done experiments.
Yeah, sure, that would be nice to do. I kind of, my assumption's been that the blocks are going fast enough that it's probably not as important.
How fast are they going?
It's I think it was 0.25 meters per second.
Oh, okay, pretty fast.
Yeah,
Alexi.
but again, that's for computer constraint, you know.
From what is coming on the ice surface?
What?
You have water on ice surface around the ice pile, and where from it is coming? Through continuous ice and from inside the pile.
You mean in a 3D model?
Yeah,
You mean the blue?
yeah.
So it draws the water surface, and when the ice is submerged, then you see the blue.
Yeah, but is this water important for the ice breakup process?
Is it important?
Yes, because it gives additional weight on the surface.
Well, there's a little extra buoyancy, but there's no complicated hydrodynamics in the model.
No. I just ask about weight, because if you have more water on the surface, so you have bigger weight.
Yeah,
Do you count that, or it will just?
No, I'm sorry, it's not that sophisticated.
Yeah.
There's no actual water on the surface.
No,
It's just dry.
Okay.
yeah.
Okay, time for maybe one more quick question. Everybody in back happy? Revisiting some of the previous questioners. Have one more quick one? Is that allowed?
I can suggest that the water on top of the ice is taken into account because buoyancy is
Well,
modeled.
buoyancy, yeah.
So it's different
Oh, yeah,
whether
you're right.
it is modeled.
Yeah.
The ponds there are modeled.
Thank you, Yuka.
Yeah, but that was my question. But where from this water is coming? If you have continuous ice sheet, it cannot penetrate from below. If it is
don't have
going from the
continuous-
pile or
Yeah, but come on, you've
The
got the
pile.
rubble pile there, and the water can come over the.
And that's what we
it's
see
not so
also.
simple for water.
I know what you mean. In a physical experiment, you see the sheet depressed below the
Yeah,
water.
yeah, it is not immediately.
Yeah, but it's not that sophisticated. It's a simple model.
So your buoyancy spring is just a little nonlinear spring.
Yeah,
So when it's fully submerged, the force is constant.
that's right.
But when it's not fully submerged, it's linear.
That's right.
All right. Well, Mark, thanks a lot. That was